session I'm going to be talking about what happens when two waves interfere with each other and what results when these things take place. So wave interference. First of all, let's imagine when two waves meet, they by definition interfere, and if they meet exactly in phase, that means the amplitudes add up together to produce larger crests and troughs. Visually, if I have these two waves here, which we see are in phase, that means that what I'll have is something known as constructive interference. It constructs a wave with a larger total amplitude. So that's the perfect positive outcome. If two waves meet and they're exactly out of phase, so that means that the peak is aligned with a trough, then what happens is we get what's known as destructive interference. Here what happens is that the interference cancels out, and so therefore there's no wave that goes on. And in between these are the two extremes, we get a range of interference. This interference is thought about as the principle of superposition, stated as when two or more waves pass through the same location, the resultant displacement of any point is equal to the vector sum of the displacements of the component waves. Basically, you add up the displacements. Normally we'll think about, or the examples often given, we think about two waves which are perfectly with the same frequency in a similar phase, or just directly out of phase. But this situation works with all types of waves. Here we see wave 1 in blue and wave 2 in pink. And what you can do is at any moment in time, if you add up the displacement, so you work out the location, and then what you see is the addition of those two waves gives me a new wave, that black wave, which is the superposition of those first two waves. So that's a situation you may come across. When it comes down to it, it's just thinking about it and considered addition. Okay, so considered addition. Interference takes place with all types of waves, but for light waves to interfere, they must be very, very similar. Okay, for this to be able to work successfully and for us to be able to visualize it, I think is the key thing. So what we do is we use a single source of monochromatic light, so light which gives off one frequency of light, and split it into two waves using a diffraction grating. So it's just a grating with two slits in, quite close together. The light that comes out of each one of these slits is known as coherent light, because it has the same frequency and the same phase, which is coming from a slightly different original position, or a source as it like to be known. And as it happens, there was a physicist called Young who first performed what's now a classic investigation about the interference of light back in 1801. It's often known, and if you look up any books, known as Young's slits experiment. What happened there, if we think about it, we had a key source of light. From that source of light emitted and went through two separate slits. Now from each of those slits, slit 1 and slit 2, they became sources of coherent light. And what we can see is, if they're close enough, that means the diffraction of light coming from each of those two sources will eventually overlap in an area. And in that overlapping area, we get interference between the two light sources. This interference produces in the end, when it's constructive interference, we have bright fringes, and destructive interference, we have dark fringes, where that light has been cancelled out. And you can clearly see these fringes forming. There's some rules and laws to do with the size of these fringes, but thankfully we don't need to study that for standard level physics. But when it's projected on a screen, it will look a little bit like this. Now this pattern is formed due to either the constructive or destructive interference caused by the different distance from each slit. So the path length means that the two light from each of the sources ends up being slightly out of phase. When it's perfectly out of phase, that means we get destructive interference, and when it's perfectly in phase, we have constructive interference. Now just remember, for it to be perfectly in phase, it doesn't necessarily have to be at the one point when it's exactly the same distance apart. Because what we find is that there'll be another fringe, bright fringe, where constructive interference is taking place, because we'll find that the path length allows one more complete wavelength to be taking place. So again, when they interfere, they're in phase. So that's what we'll see, and that's what you observe when you're talking about the interference of light.